Welcome to this explainer. Settle in because today we are completely tearing apart the complex, dynamic forces that actually shape our coastlines. If you just stand on a beach, it kind of looks like a pretty static boundary between land and sea, but it's actually a highly active, constantly working machine. Let's dive right in and uncover the hidden gears of our shores.
Here is what we're covering today. Dynamic systems, what are sediment cells, the power of boundaries, open versus closed systems, how fine sediment escapes, and finally, the impact of time. Section 1, coasts as dynamic systems. Like I said, to truly understand the beach, we have to stop looking at it as just a place and start seeing it as a massive, breathing engine. Think of it like a giant glowing flowchart. You've got energy and materials, like sand and rocks, entering as inputs. Maybe they come from the land, offshore sources, or even human activity. Then, powerful coastal processes transfer and move all that material around. They get held in stores, which are literally the beaches and dunes we walk on. Eventually, materials leave as outputs. And this entire furious sequence is happening within a very specific boundary. Part 2. What are sediment cells? So how do we actually define these systems out in the real world? Well, to put this into perspective, around the coastline of England and Wales, there are exactly 11 major regional sediment cells. The entire coast is carved up into these 11 distinct zones. A sediment cell is basically a stretch of coastline where the movement of coarse material is completely self-contained. The sand and pebbles are locked into their own geographic loop. They just circulate around without ever really crossing over into the neighboring cell. Section 3. The power of boundaries. You're probably wondering, what's stopping all that sand from just washing down the whole coast, like a giant conveyor belt? It's all about the boundaries. The walls of these coastal rooms aren't just invisible lines on a map. They are massive physical gatekeepers. We're talking about prominent rocky headlands, places like Beachy Head, Selsey Bill, or Portland Bill down in Dorset, or even massive water features like the River Severn estuary. These are the absolute guardians of the system. Picture a massive headland jutting aggressively right into the ocean. Those brilliant white chalk cliffs aren't just there for the view. They act as an immovable natural barrier, physically cutting off the flow of waves, energy, and all that material dragging along the shore. Which brings up a really crucial question. We know how longshore drift works, right? Swash pushes material up the beach at an angle, backwash pulls it straight down in a continuous zigzag animation. But what actually happens when that relentless energy smashes into an immovable boundary? The answer is simple but profound. Sediment accumulates. The headland just blocks the transfer like a giant brick wall. The heavy stuff piles up, the beach widens on one side, and boom, it proves that this specific cell is operating as a fully contained, restricted unit. But how is it moving before it hits that wall? Well, when the sea gets energized, it picks up or entrains the sediment. Heavy boulders are literally dragged along the seabed in a process called traction. Lighter pebbles bounce along via siltation. And the absolute finest particles, they get swept up and travel entirely suspended right in the water column. Section 4. Open versus closed systems. If headlands physically block the heavy stuff, how do we actually classify these cells? Are they completely sealed off? Let's get our definitions straight first. An isolated system exchanges absolutely nothing. A closed system exchanges energy, but no physical matter. And an open system freely exchanges both energy and matter across its boundaries. Because those giant rocky headlands do such a phenomenal job of blocking coarse physical materials like pebbles, researchers historically called these sediment cells closed systems. Energy crashes in and out, sure, but the heavy physical matter stays locked safely inside. Section 5. How fine sediment escapes. You see, nature is rarely that rigid, and this sparks a massive debate. Are these boundaries really truly closed? Just look at the stark contrast here. On one hand, you have massive, heavy pebbles on Chesil Beach that are incredibly easy for headlands to trap. But on the other, you have ultra-light, fine silt, like the cloudy, turquoise plumes escaping into the Gulf of Alaska. That fine sediment doesn't sink. It just hangs there, suspended in the water.
So, sediment cells basically have a dual identity. They're closed systems when it comes to heavy rocks hitting physical walls, but they are totally open systems for fine, suspended sediment. Silt is just too light. It gets swept right past those flickering boundary lines by powerful tidal currents and crazy storms.
Section 6. The impact of time. To really master this concept, we have to add the ultimate variable to our system's model: time. Because the coast is never static. Coastal landscapes operate on wildly different timescales, all at once. A violent rock fall from a cliff happens in seconds. Beaches grow and shrink over days or seasons, depending on the weather. Brand new landforms like spits take years or centuries to form. And across millennia, we get massive shifts in sea level due to ice ages. The whole system is in constant temporal flux. Because time introduces so much chaos, a sediment cell is never perfectly average. A massive, exceptional storm can drag material so far offshore that it completely escapes the cell. And then, well, there's us. Hard human engineering, like dropping massive concrete breakwaters at Brighton Marina into the sea, artificially acts like a brand new headland. We literally interrupt longshore drift, starving one side of a beach while piling up sand on the other. I want to leave you with this provocative thought to ponder. We've seen just how delicate the balance of inputs, stores, and outputs really is. So, as we keep building artificial barriers, and as climate change throws wilder, higher energy storms our way, will any sediment cell remain truly closed in the future? Thank you for exploring the incredible mechanics of our coastlines with me today. Keep looking at the world as the remarkable, dynamic system it really is.